In today's lecture, we're going to start going into Lecture 3, which corresponds to your textbook, Chapter 3. Chapter 3 focuses on one very important issue in digital circuit design, which is methodology. We're going to teach you systematic designing procedures to design digital circuits. The designing procedure will prepare you, first of all, to understand specifications for a particular circuit design requirement, and then break it down into separate steps so that you can follow and then design the subsequent circuit as required. Recall what we've did in Lecture 1 and 2. Lecture 1 is actually all about how information is represented in digital or logical circuit, as well as what exactly is digital or logical circuit. Namely, information is represented in digital circuit with binary signals, and these binary signals are represented inside your digital circuit using voltage values. The voltage values are divided into a high voltage area and a low voltage area. By using these values, you can basically represent any information you want. We've shown you numbers, we've shown you letters, and in the future you will also encounter stuff like fraction numbers, such as float numbers. In Lecture 2, we discussed the basic components that you can use to design a digital or logical circuits, namely the gates, as well as some very simple I/O devices. In our examples, the only I/O devices we care about is in LogicWorks, the binary switches and the binary probes. In Lecture 3, we're going to encounter a few more different ones of these I/O devices. Aside from that, we also discussed Boolean algebra, which aims at optimizing individual circuit designs, optimizing the Boolean expressions so that you can implement a specific circuit as efficiently as possible, using the least amount of physical components as well as, just physical components. So, the primary objective of Lecture 3, as we have discussed before, is centered on methodology. It's answering two different questions. First of all, how to systematically use what you've learned in Lecture 2. So Lecture 2 taught you the basic stuff. We have the truth table, and usually what you would do if you want to design a system is, first of all, you obtain the truth table, and then you go from having the truth table to having Boolean expressions. And then further simplified into simpler Boolean expressions, you can then take into LogicWorks and implement them. Now in Lecture 3, we're going to expand on that by first of all defining systematic designing procedures. So there's the methodology over there, and we're also going to take you through a lot of the practices which uses these systematic designing procedures. So, first of all, let's talk about the systematic designing procedures. It is very important, regardless of what you're doing, when you try to start designing something, be it a user interface, be it your website, be it the backend of your website, for example, or in this particular case, a logical system. The most important thing when you're starting is to know exactly what you want from the system. And this, as we refer to it as the specification of the problem. You need to understand the problem, what exactly is desired. All of the technical details, you will need to understand them first. Once you have a thorough understanding of exactly what kind of system you want, you'll want to draw up a very basic design. The basic design will fulfill all of the functional needs of your system, but it's actually a little bit too, it could be a little bit too cumbersome to implement. For example, it's using 100 different gates to do something, in which case it could be a little bit difficult to design or implement in LogicWorks as well as in real life. So the next thing you would want to do is to apply optimization. Now the process of performing optimization comes in a few different stages, which we're going to introduce you. But basically, optimization is take your basic design and move one step further. take the basic design, apply K-map optimization, binary identity optimization, as well as performing optimization using some of the later techniques we're going to teach you, you make the overall design simpler and easier to implement, as well as easier to find problems, debugging basically. So let's take a look at the systematic designing procedures. These systematic designing procedures are universal, which means you can use them to design any digital circuit so far. Now, as you can see over here, we have 5 different steps. First of all, you have specification, which deals with knowing exactly what the problem you're solving, and usually the specification is what we're going to provide to you, in this course at least. Followed by specification, you have a formulation. Now, formulation refers to deriving the relationship between inputs and outputs of the system. So it's transforming the specification into either mathematical expressions in Boolean algebra or transforming specification into a truth table. Regardless, both the truth table or Boolean expression is describing your basic specification need of the system. Followed by formulation, you would obviously already have either a truth table or a set of Boolean expressions, which basically maps out the relationship between your inputs and output ports. The next thing you will need to do is to apply optimization on either the truth table or the set of Boolean expressions. If you're starting with the truth table, the first thing you will probably want to do is to take out the sum of minterms and then use binary identities, K-maps, to reduce them, to minimize the number of logical gates and literals required. If you're starting with a Boolean expression, well, the job is a little bit easier. You will simply use Boolean identities to try to simplify all of the Boolean expressions. The next step is called technology mapping. Technology mapping deals with existence of physical components as well as pre-implemented subsystems. This is something that we're going to spend a lot of time discussing. For now, let's just remember that technology mapping is the step that you take your Boolean expressions, bear in mind already optimized, and use physical components to implement them inside either LogicWorks, a simulator, or, as we see in real life, production prototyping, I guess. And finally, last but not least, just like when you're practicing doing programming languages, it is very important that you try to verify the correctness of your final design. In this course, we're going to primarily focus on the first 4 procedures. Verification comes in a wide variety of different methodologies, and it is not uncommon for us to rely on computer automated verification systems. This is all something very, very advanced. For us, verification simply is the stage that you take either the truth table or original Boolean expressions, or you can even go further back, take the specification and then apply the specification or truth tables on your designed system to find out if it actually works as intended. So for now, for us, verification is simply that. In the future, if you're curious, if you do decide to work with digital circuit designs, verification will usually involve automated systems which automatically go through all of the truth table rows that you have predefined and then check the output against the output on the truth table. That is one of the things that you could do. You could also have unit tests similar to programming languages in verification, also completely automated. But for our course, verification, as we said before, is the simple process of using the truth table or simply the specification to verify the correctness of your final design. Trial and error. So, With that little bit of understanding of the 5-step systematic designing procedures, let's take a look at an example. This example is mentioned in one of the previous lecture slides in lecture 2, in which you are designing a curtain motor. Now, first of all, let's take a look at the specification for this problem. Over here, your primary objective is to design a curtain motor control unit. The curtain motor control unit comes with a few different parts. It comes with 2 different sensors. Sensor 1 is going to give out a positive signal if the curtain is already fully closed. And sensor 2 is going to give out a positive signal when the curtain is fully open. The basic idea is if the curtain is already fully closed, you can't rotate the motor to close it further. And when the curtain is fully open, you will not be able to rotate the motor further to even, well, open it further. You also have 2 buttons where the user could provide its inputs. The user could choose to press button 1 to open the curtain. Now, the curtain will be in an opening position if the curtain is not fully opened, of course. And you also have a button 2. Button 2 is going to give out a positive signal if the user is pressing it with the intention of closing the curtain. Now, again, if the user is pressing button 2 to close the curtain, and the curtain is already fully closed, you can't keep rotating the motor. That would not be very good for your motor, for your entire system. And aside from these, you also have output 1, which is a motor control signal. Output 1, if the output signal is positive, it will make the motor rotate to open the curtain. And output 2 is going to be positive if you are making the motor rotate to close the curtain. And finally, you have an indicator light, which is on when either motor, either output 1 or 2, is active. So as long as the motor is rotating, whichever motor it is, your light should be on. And obviously on the right hand side, we have the condition. If the curtain is already opened and you try to open it further, the motor should stop. And if the curtain, well, you're trying to close the curtain and the curtain is already fully closed, then the motor should also stop. Now, let's try to apply the 5-step systematic designing procedures in this particular case. Step 1, we have specification. Specification deals with the inputs and outputs as well as their relationships inside the problem description. So in this particular case, the most important thing is to identify the set of input and output signal ports. For us, this is very simple. We can very easily identify sensor 1 and sensor 2 as providing input to the control chip, and then output 1, output 2, and the light providing outputting output signal to the curtain motors as well as the light. And then you have button 1 and 2 also as input from the user. So this system, the control unit, quickly becomes a system that you need to design, which takes 4 different inputs. The 4 different inputs will have different names, of course, sensor 1, sensor 2, button 1 and button 2. And then on the output side, you also have 3 different ports, output 1, output 2, as well as the final light. In all of our examples, as well as all of our implementations in LogicWorks, the only input and output devices that you're going to be required to use is the binary switch as well as the binary probe. In the future, we're also going to teach you how to use something like LED displays, but that is something reserved for later lectures. For now, for all of the implementations, you can simply use binary probes and binary switches for output and input. So here we are. We have 4 different switches for 4 different input channels and 3 different binary probes for 3 different output channels. And on the right hand side, you have one additional condition which we will transform into either Boolean expression or truth table in step 2. So now, with all of our knowledge in the specification of the problem, I hope you have a good understanding of our primary objective, the control chip that we're designing over here. And then let's take a look at step 2, formulation. Step 2 formulation has 2 different approaches. You can either try to transform all of the specifications into truth table, or in this particular case, you can directly try to do the Boolean expressions, which arguably sometimes could be a little bit simpler. So in this case, I'm going to try to convert all of these specifications into Boolean expressions. So the first 2, sensor 1 and sensor 2 is essentially giving out signals to tell you if the curtain is fully closed or the curtain is fully opened. For that, I can define 2 different variables, fully closed or fully open, here to be equal to sensor 1 and sensor 2 for my own convenience, so that it's easier to understand for me. So in this case, if the curtain is fully closed, sensor 1 will give out a positive signal, which in terms is transferred to fully closed. If the curtain is already fully opened, this will trigger a positive signal in sensor 2, which is then transferred to fully opened. Next, let's tackle one of the easier examples, the light. So the light, as you can see, the light is going to be on when either motor is active. So the either motor will be output 1 and output 2. If either output 1 or output 2 is giving out a positive signal, then the light should also be positive. Over here, we can simply use a OR gate or OR operator to signal that relationship. Light equals output 1 or output 2. If either output 1 or output 2 is 1, which means the motor is either trying to open or close the curtain, then the light should be turned on. Otherwise, when both motors are inactive, the light will obviously be equal to 0. The next thing we can do is to try to model output 1 and output 2. Output 1 and output 2 both have 2 different conditions. First of all, if you want to open the curtain, the user must be pressing the button 1. And further, if you want to rotate the motor to open the curtain, the user will have to press the button 1 as well as sensor receiving a positive signal saying that a negative signal saying that the curtain is currently not fully opened. So basically, the condition for output 1 to be positive is when button 1 is pressed and fully opened is at a state of negative. So it's not fully opened. Output 2 is similar. If you want to rotate the motor to close the curtain, button 2 should be pressed and the sensor should be telling that this curtain is currently not fully closed. So that basically covers our 2 outputs. And finally, there's one additional thing that is hidden over here. What if the user is trying to press button 1 and 2 at the same time? And now I'm fairly certain that in a younger age, when you had the primitive TV remotes with increasing channel or decreasing the channel number, you have obviously tried to press the both buttons at the same time to see what would happen. Now for our system, something like this is also going to be added to the system. when button 1 and 2 are both pressed, what I want to do is I want to deactivate both motors at the same time. This is optional, but this behavior is what I would define right now, just to prevent the uneventual case that this current control unit is passed to a child like ourselves, and then we decide to do something naughty. So, first of all, we need to detect when the two buttons are pressed at the same time. We use a new variable called both pressed, and then we invert the signal so that this would generate a negative signal when both button 1 and button 2 are pressed, so that it can further disable output 1 and 2. Again, using your basic binary identity, anything and 0 is always equal to 0. So, in this case, if both buttons are pressed, regardless of the state of fully open and fully closed, both output would be disabled. Both output would be generating a 0 value. And that covers all of our conditions, all of our specifications. Now, with this nicely formulated Boolean expression, in the next step, we can simply go to optimization. What I would do over here is I will quickly perform some optimization. First of all, I'll bring in the value for variable fully closed and fully opened into output 1 and output 2, and then I'll bring in the value for both pressed into output 1 and output 2. This will obtain for me the binary Boolean expressions for the three output channels, light, output 1 and output 2, and as you can see, only the input variables are used on the right hand side. Once this is completed and we realize that this is already as simple as it gets, the next thing we can do is we can do technology mapping. Now this is where it gets interesting. The step technology mapping, the first thing you will need to do is you will need to know what kind of physical components are available to you. And this is called technology. The physical components are called technology. On the left hand side, you have purely a mathematical representation of your system. And on the right hand side, we have the physical representation that we will need to do in technology mapping. So let's assume that in this case, you have access to the following gates. You have access to AND gates, NAND gates, or NOT gates, as well as binary switches and probes for input and output. What you will need to do is you will need to use only these components to try to design and implement your circuit. So in this case, I can do this very easily and show you the results. Here we have used a NAND gate, 2 AND gates, 1 OR gate, and 2 NOT gates. On the left hand side, we have all of our input. Each of them you can use a binary switch in LogicWorks. We're going to show you how to do that in a separate tutorial video. And on the right hand side, you would use in LogicWorks binary probes for all of the output channels, 1 each. The reason why the concept of technology mapping is so important is because in reality, you might have more components at your disposal, or in certain cases, in the unfortunate events, you might have less components than you would desire. So for example, let's take a look at the cases where you do not have a NOT gate. If you do not have a NOT gate, you would need to come up with alternatives for both NOT gates in this particular circuit drawing. You will need to replace them. Now, one of the simple replacement of a NOT gate is to leverage the existence of a NAND gate. You can replace a NOT gate with a NAND gate and then attach the other input to a positive signal, because we know a variable x and 1 is equal to x, and then the NAND gate will also have a NOT gate at the very end of it, the tiny little dot over there. So even though you don't get the NOT gate, you still have NAND gates at your disposal. which you can use essentially to replace the NOT gate. This replacement unit would work exactly the same as the NOT gate, and this is what you might encounter, although very unlikely in this particular manner without a NOT gate. But this is in fact something that you would probably encounter in technology mapping. Sometimes you have less components available to you, and sometimes you have more alternatives to choose from. And in this case, when you're trying to go from having the binary expression to implementing the physical circuit, you will need to very cleverly only use the available components and try to make do. Now, as I said before, this is only a hypothetical situation. It's very unlikely in reality that you will not be able to find NOT gates at your disposal. So let's turn our back into the original implementation over here. And then step 4 is completed. We can proceed to step 5, which is verification. In this particular case, the simplest verification you can do is to look at the specification and try to press some buttons and give the sensor inputs and see if your output is indeed correct. I've listed a couple of test cases on the right hand side. You can have sensor 2 is positive, button 1 is positive, which means the curtain is fully opened, but you're still trying to open the curtain. In this case, both motors, output 1 and 2, should be 0, and the light also should be 0. The next step, you have sensor 1 and button 2 being pressed. So this is basically showing that you should be closing the curtain, and the curtain is already fully closed. So both motors should not give out positive signals. And the next thing, both buttons are pressed, only one button is pressed, and so on and so forth. You need to run through all of these test cases to see if your circuit is actually working as it should. And that is the entirety of step 5. So looking back, we have, again, this is called the 5-step systematic designing procedures. We have step 1, specification, for which you have a textual description of what your system is supposed to do and list of inputs and output ports. Step 2, you have formulation. Formulation deals with transforming the specification into mathematical representations, either a truth table or a set of Boolean expressions. Step 3, you would take the truth table or Boolean expression and perform optimization so that you're using the minimum amount of Boolean literals and binary operators so that it's easier to implement, essentially. Optimization, simplification of your Boolean expressions. Next up, you have step 4, which is technology mapping. You're taking a look at the physical components you have and then transforming the mathematical representation of your system into physical implementations or physical simulations in LogicWorks, let's say. And then finally, step 5, you're trying to establish a series of test cases according to your specification or truth table, and then you run through all of these test cases to make sure that your system is indeed working as it should. Now, so this is where this video ends. A tutorial video will follow. Thank you.